again, Stuart from Berkshire Guitar Amplifier Repairs in Reading, England, and on the bench we have a JCM800. Apparently it's a JCM800 lead split channel. Okay, now this one I haven't been looking forward to working on, and to be honest with you, I've put it on the back burner, but I've shucked up my pantyhose today and I thought I'll have a go at it. The problem with it is, apparently it works fine. The customer uses it via an attenuator. Ugh, an immediate negative there. I hate attenuators. They stress the amplifier. You think you're playing reasonable volume, but you're actually maxing the amplifier out, flat out. It's not good for it, but anyway, that's just a pet peeve of mine. And apparently after playing it for a while, it kind of runs away. He says the bias runs away. I don't know if he knows that's true or not, but anyway, the bottom line is it ends up blowing an HT fuse. So what I think we're going to have to do with this amp, I think I'll power it up and just see if it works. I'm sure it does. Then we're going to need to get the chassis out, get it under load, stress it quite a lot by making it run at 30 watts or so, and keep an eye on what's happening to the bias via a couple of bias probes. I think that's about all we can do on this. Theories at the moment, well, it could be runaway bias, but I don't know why that would suddenly start shifting. Let's not speculate. Let's power it up and see if it works, and then we can get the chassis out. Okay, I checked the fuse, it was okay, and then I noticed that the loudspeaker lead was dangling down inside the amp and hadn't been plugged in, so I'm not quite sure why that's been unplugged, but anyway, there we go. See if we get any more sense now out of it. Still very quiet. Oh, it's coming up now. Okay, there we go. Yep, that's come up. That's working okay. Yep, that's fine. A bit buzzy. Listen to that racket. Ugh. Ooh. Okay, I've pulled the chassis, and it's a very lovely, clean example of this amplifier. It looks absolutely immaculate. I've had a little look around with the eyeglass and there's nothing at all obvious. Here's the bias circuit, of course. Here are our bias smoothing capacitors, bias adjustment pot. These look good, no sign of any leakage. So I don't think there's much we can do here apart from get some meters on and see what the bias is doing. Right, I've got a couple of bias meters in. I've got one on stage and one off stage, and we'll turn on the HT. We've got 43 milliamps on this valve and 37. This one's very hard to read on the camera, it's very dim. 37 milliamps on this one, so they're a reasonable pair. So I'm just going to make a note of those two bias currents. 43 milliamps on this one and 38 on the other. Now if we have a bias problem, I would expect to start seeing these drifting regardless of what signal's going through here. Yes, it might be worse when you hammer the amp, but I would expect to see some sort of drifting going on here with the thing just sitting here. So I'm just going to leave it on for a little while and see how stable it is when it's just sitting here. Right, you join me 15 minutes later and this valve is 46 milliamps. It was 43, and the other one, which you can't see, is 42. It was 38, so that's exactly what I would expect with the amp being on for a while, a slightly increasing bias current. So nothing dramatic's happening here. It's not like we have a problem and the bias just runs away. I'm going to leave it on for another hour. just to double check that. So I'll join you back in 1 hour's time just to make sure that these are nice and stable. Okay, it's been on for about an hour in total and nothing's changed. So we've got 45 milliamps on here, and on the other one it's 41 milliamps, so very little change at all. So whatever this is not a drifting bias problem under normal circumstances. So I'm now going to put the amp onto a dummy load, and I'm going to put a sine wave through it, and I'm going to aim to get about, I think initially about 10 watts ticking through the amp, and we can see if anything changes as a result of that. Here's my dummy load. It's just a few power resistors onto a socking great big heatsink. So I'm going to connect that up to the output. Like so. And then I'm going to put my oscilloscope on the output so that I can monitor the output peak to peak voltage. I'll show you that in a moment. And then we'll plug the signal generator in front. Like that. Okay, there we go. We've got a nice signal coming out. So let's replace the speaker with the load. Turn up the signal, and there it is on the scope. Right, I'm just going to work out what 10 watts is in peak to peak voltage, because I've just forgotten, and then I'll let you know. Right, I've just done the sums, and 25 volts peak to peak into 8 ohms, it is about 10 watts. So that's what we're going to set. We're going to set 25 volts peak to peak. So there's the signal generator feeding into the input of the amplifier, and here is the output signal coming off the load, the 8 ohm load. It says 500 millivolts there, but I've got a times 10 probe, so that's actually 5 volts. So each division is 5 volts, 5, 10, 15, 20, 25 volts peak to peak there, and that's roughly 10 watts in the amplifier. Here's the load. Should be able to feel it getting slightly warm, which I must admit I can't at the moment. Right, now the bias meter is showing 62 milliamps. That's going to be a kind of average current because now we're putting AC through the output tubes. So we would expect the harder the tube's working, the more current is going through it. Don't forget, bias current is just a steady state DC. If I turn the signal generator down, look, that just reverts to its standard 45 milliamps DC. If I make it take 10 watts, the average current is much larger. So I think the thing to do now is just leave that sitting there for a while. The only thing I would say is that the HT is a bit lower than I would have thought it might be. 360 volts HT on an amp like this. I would have thought we'd have a bit more than that, more like 450. So that might need investigating. Anyway, let's just leave it ticking away there for the moment. And it's nothing to do with the fact that we're putting a signal through it, because if I turn the signal off, that it does go up a little bit, but not significantly. And that is the HT I made a note of when we started anyway. So I've just got a question mark over that in my mind at the moment about why that's so low. The other thing is, let's put this on 10, 20, 30. Let's see how much power this amp can deliver. Not much, so 10, 20, 30, 45 volts. I won't leave that up there too long. Yeah, these are warm now, so that was putting out 10 watts. I'm going to turn this off for the moment. And let's work out 45 volts peak to peak. Let's work out what power that is. Yes, I've just done the sums, and this amp is developing about 27 watts maximum, and that would be about right if the plate voltage was down by at least 25%. So something screwy here. Now what I'm going to do is pull the power valves out and check the HT again. I'm going to get the amp upside down and check the HT on the underside and just make sure it's not the valves doing something. I can't imagine what. We know what the bias current is, so they can't be killing the HT. We could pull the preamp valves. I'll be very surprised if they're doing anything. So basically, if this amplifier hasn't got a decent HT with all the valves out, we've got ourselves a problem. Alrighty, well, we've got all the valves out, and look what we got here. Chassis. I'm going on the HT caps now. 390 volts, 390, 385, 380. The HT is 100 volts lower than it should be. Why? This is an interesting question. Well, here's something weird. Here are the rectifier diodes for the HT, and this diode here is for the bias, so let's just ignore that for the moment. There should be 4 diodes in here for a full wave rectifier. At the moment, this is being half wave rectified by 2 diodes. These 2 diodes are missing. They were here at one point. I can see where the solder is underneath. So for some reason, D8 and D9 have been removed from this amp. I have no idea why that is. I don't know whether it's supposed to be like that. I'm going to need to do a little bit of research to find out, but that would certainly account for our low HT. If we popped 2 diodes in there, I think the HT would come back up. Okay, I seem to be wrong on this. Here's the schematic for the amp, and here are the windings. This is the HT winding here, the centre tap of which is taken to ground. And I don't know why they've put these 2 diodes in series here. Don't quite understand that, but anyway, think of that as one diode. So we've got one diode going to HT and another diode going to HT as the polarity of this goes up and down, or reverses I should say. So they haven't used a full wave rectifier on this, so this is kind of how it's supposed to be, I guess. So the next thing we really want to do, I guess, is to measure the AC input coming in here to see how much voltage the mains transformer is giving us. So we'll go on to HT, we'll go on to AC and turn it on, and we can measure, where can we measure the AC? Across these 2 parts of the diode here. Well, 578 volts, so make a note of that, 580 volts AC. Coming in. And of course from ground to any one of these would be half of that, so 287 volts on each side. Okay, follow me through on this. So the meter's set to AC, and on each side of the winding from ground we've got 286 volts, and the same on this diode here, 286 volts. So assuming that this meter measures RMS, we've got 286 volts RMS. To convert to peak, we're going to multiply by 1.414. It makes 400 volts peak on each of the halves. So 404 volts is the maximum we could get into DC into the capacitor. Of course, if we load that, that will start to come down. And that's about what we're seeing. I mean, it's 380 or something, it's not a million miles off. And there's no load on there. So I don't believe we have enough AC voltage coming into here. Okay, I've turned the voltage selector on the back to 220 volts. It was on 240. And as you can see now, we've got another 5% of HT there. Still not as high as it should be. Just a little experiment, a rather interesting experiment. I'll put that back onto 240. Right, excuse the lash up, but I just wanted to make sure I wasn't fooling myself here. I've got a mains transformer which is fairly standard for any kind of Fender amp, that type of thing. It'll easily handle 6L6s, EL34s, it's got all the usual tappings on it, and it's just a spare one I've got. I've got it hooked up to my mains connector here, so the primary is going in on the white and the black, and I've got the HT, one side of the HT going to the meter, and the center tap, that's the yellow, going to the meter too. So now I can measure across one winding, and when I close this here, look what happens. I get 368 volts AC across one half of the winding. Now remember, that is RMS. So let's do the calculation to translate that to peak voltage. Well, there's the sum there, 368 volts AC. You multiply by 1.414 to get the peak, or peak to peak, and that's 520 volts. So in theory, we could rectify that and get 520 volts DC from that transformer. In practice, by the time you've lost a little bit and current starting to be drawn, you'll get 470, 480, 490, which is exactly the kind of voltage we would be expecting. Now, just to remind you, on our mains transformer here, we're getting 287 volts there instead of 368. So that just proves that the transformer is currently giving low voltage for what we need, and we just have one more thing to do. I don't know why the transformer, by the way, it's this transformer here, I don't know why that's giving low voltage. The only thing I want to do is to completely disconnect the HT winding from the rest of the amplifier. At the moment it goes to the diodes and it goes to the smoothing caps, that's the only place it's going. But I want to completely eliminate anything pulling down the HT. I mean, for example, highly unlikely, but imagine if one of these capacitors was passing some DC current, it was leaking inside, and it was just pulling a steady 100 milliamps or something like that. That would load the secondary winding here and bring down the AC voltage. So that's the only test we have left to do, and that will prove conclusively whether it's the mains transformer or whether it's something to do with the rest of the Right, I've disconnected the HT from the rectifier diodes to the smoothing capacitors. This is it hanging off here. So there's now nothing downstream of these diodes. Let's turn it on and see. And we're going to be again checking, just like we did on the other transformer, we want to check what the AC is coming in here. So it's from the center tap of the HT, which is ground, coming in here. I think it was switched off, so coming in here, yes, there we go. Again, look, we've got our 283 volts, which is no good at all. 283 volts there. Remember, we had 368 on the other transformer, so we're well down. We've disconnected everything downstream. So there you go, we've got a mains transformer which for reasons unknown is giving out a low HT voltage. I have no idea why that is. Could be a wrong transformer. I don't think it's anything to do with the voltage selector being wired incorrectly, because we only have a few choices there anyway. We have 240, 220 and 120, and you know, the 240, when I changed it to 220, the voltage came up in exactly the proportion I'd expect it to. And I'm certainly not going to go on to 120 because that will give us double the voltage. So I don't think it's the voltage selector or the tappings on the transformer. So I'm going to restore all this, and we need to find out what the customer wants to do here. Right, I've restored everything to normal, and here is the mains transformer. It's a Drake Transformers 1202-324/2. The fact that the output transformer is also a Drake transformer makes me think these are probably original, and so is the choke. That's also a Drake transformer. So why we have a problem here, I don't know. Could it be a partially shorted HT winding or something? I'd have expected to have some arcing or something going on inside if that were the case. But something wrong about the voltage this transformer is putting out. And also I think I ought to check the heater voltage out, the 6.3, to make sure it's 6.3, and that's a good idea actually. That would be a good way of telling whether the primary winding is correct on this. In other words, if we've got the right 240 volt tap. So yeah, let's do that. Okay, the amplifier is on. I'm going to measure on the heaters. Doesn't matter where we go. And what have we got? We have 6.3, 6.4 volts AC on the heaters. We don't even need to measure the AC input. We will, just for the sake of it, but we know it's going to be 240 volts or whatever it is. 240 volts, look. So that's told us quite a lot. I wish I thought of doing that earlier actually. The mains voltage coming in is okay. The heater voltage is exactly right, which tells us we have the correct primary winding for this transformer. It's not some mess up with the primary connections. And yet the HT coming out is too low. Okay, I found out something about this transformer. 1982 Drake 1202-324/2, which is what I've got. 50 watt power transformer. This power transformer has a lower B plus than the 1202-1 or the 1202-3. Some early Marshall amps used lower B plus transformers. I wonder why. This power transformer is 303 volts 0, 303 volts, giving a B plus rectification of 400 volts. So that's very interesting. So we weren't getting 303, but we were getting 287, 290. That's not far off. And we weren't getting 400 volts, but we were getting, I can't remember what we're getting now, 370 or something like that. So I'm wondering if for some reason that I don't understand, we are stuck with a low plate voltage on this amplifier. And we might have been chasing a ghost. I've never seen a Marshall with a 370 volt HT, but it looks like we got one here. Right, good morning. I've taken a 24-hour break from this amp just because I spent several hours down what seems to be a blind alley. I think I'll leave it all in because I've learned something from this, so hopefully you will too. The transformer, the mains transformer in here, is a Drake 1202-324/2, but you knew that anyway. Apparently, and it was very, very hard to find out, this transformer gives a lower HT voltage than either the 324-1 or the 324-3. What I cannot find out is why Marshall fitted this amplifier, in other words why they wanted a lower HT voltage. Anyway, the maximum possible HT out of this is 400 volts, and that's on a good day with a following wind. We're getting no load. I'm getting 385 volts, that's with all the valves pulled. So we're a bit down on what it should be giving, and by the time we get some valves in and start loading the transformer a bit, we're getting this 369 plate voltage here, so 370. So this amp is running on a very low plate voltage. Don't know why. There you go. I'd expect another 100 volts on there, and every other Marshall I've worked on will give like 460, 470 plate volts, sometimes up to 500, so I've no idea. It's lost in the midst of time. So we've gone back now to looking at the amplifier, and you know, the customer's main complaint on this amp is that it sounds crappy when it's driven, in other words when it's cranking out the volume. I don't know what sounds crappy means, but anyway, we can measure crappiness with our crappiness detector here. And so what I've got it set up on now is I'm on the clean channel, and I'm going to turn up the signal generator until I get squaring off of the output. So here we go, and it's just going there. I'll just turn up the volume on the actual amplifier a bit actually. Where's the master? No, that's on full. Okay. Yeah, we'll turn up the volume here, and there we go, that is actually squaring off there, look. Let's just back it off a touch on there, and I've got 1, 2.5 divisions there, I think you'll agree. I'll turn that down, we don't want to be running the amp flat out. So 2.5 divisions at 20 volts per division. I've got a times 10 probe, and it's 50 volts peak to peak. So let's do the sums on that and see what the amp is producing. Actually, just before we do that, let's also notice that the output is nice and clean. So in other words, there's no, our crappiness detector here is detecting nothing, even when we got quite high levels. That's a nice clean sine wave on the clean channel. Now let's go on to the crunch, well, gain channel, or boost channel as it's called. This light has come on. We've got a more distorted signal here, which is what you'd expect. Just turn that down a bit. So you can see this is more triangular, this signal, and that would sound crunchy, which is just what we want really. So the volume is up full on here, but the gain is right down. So as we turn up the gain and turn down the volume, you can see we get a sort of fairly distorted, and that will sound very distorted to the ear, which is kind of what you want really. Again, are we getting a bit more? No, we've only got 2. No, we're still only getting our 1, 2.5 divisions out of the amp, which are 50 volts peak to peak. So that all looks fine to me as well. Treble, middle, bass, well it depends what frequency I've got going in. So there you go, that is producing 50 volts peak to peak, and the signals kind of look alright to me. Our load is warm, so we are actually producing some power, and that all looks good. So let's do some sums and see what the amp is actually producing at 50 volts peak to peak into 8 ohms. Okay, to find out the power, we have 50 volts peak to peak, which is 25 volts peak, and to find the DC equivalent of a 50 volt peak to peak sine wave, we multiply the peak by 0.707. So it's 25 times 0.707 equals 25 volts peak times 0.707. For details, see the internet. 17 point, let's call it 17.7 rounding up. So that 17.7 volts is the DC equivalent of a 50 volt peak to peak sine wave, and we need a DC equivalent to get the power. So we've got effectively 17.7 volts DC into 8 ohms. Be the equivalent of putting a 17.7 volt battery across 8 ohms and asking what the power is. Well, the power is given by V squared over R. For details, see Ohm's law. So V squared is 17.7 squared divided by R, which is 8 ohms. We've got an 8 ohm load. Again, let's do the sums. There we go. So 17.7 times 17.7, that's our V squared, 313, divided by our R, which is 8 ohms, and we've got 39 watts coming out of this amp. That's the maximum it can produce. And that's not far off, I think, what it should be producing. Notice that our HT is maybe 5% down, the HT, which will mean that this peak to peak voltage here is 5% down. So let's just imagine, I haven't done this sum, just it's for my interest as well as yours really. Let's imagine that 25 volts peak is 5% more than that. In other words, the transformer's doing what it should be doing. 26.25 volts now. Let's do the sum with 26.25 times 0.707 equals... The reason I'm doing that is because power goes up with V squared, so I'm interested to see what this actually does. So 26.25 times 0.707 is 18.56. So let's do our V squared times 18.56. 344.45 divided 8 ohms is 43 watts. It's interesting how quickly that comes up, isn't it? So from 39 watts we've gone up to 43 watts just with a 5% increase. So again, this is not too far off what I'd expect from an amp like this with a couple of EL34s. Right, hope you enjoyed that. So now I've set up the amp to run at 15 watts, so we've got 30 volts peak to peak here. I won't do the sums with you, but that's about 15 watts. You can see the bias has gone up to 69 milliamps, which is perfectly okay, exactly what you'd expect. Don't forget, this has now got AC current going through, and this meter is averaging that AC current to produce this figure here. That's perfectly right, perfectly happy with that. So I'm just going to leave the amp running at 15 watts, and this should be getting warmish. It is. The resistors are warm, which is fine, because I understand that one of the complaints was, you know, if you carry on playing it loudish, then the bias runs away and it blows a fuse, but I've seen no evidence of that whatsoever. And yeah, 15 watts, if I put a speaker on this, it would deafen us. And I did understand that the customer used it with an attenuator, which is a very, very bad thing. You should never use an amp with an attenuator, in my view. That's my personal opinion. You're effectively thrashing the amp, maxing out everything, but it sounds very nice, reasonable playing volume. It's a bit like revving a car as hard as you can, but for some reason it only goes 10 miles an hour and you can't hear the engine. That would be very, very bad for the car, and that's what you do to an amp when you put an attenuator on it. Anyway, so we're producing, you know, nice sensible wattage here, which would deafen you if you were playing at this level. And I'm just going to leave it on for, I don't know, I might leave it on for half an hour really, just to double check that nothing runs away, nothing goes crazy. Nothing's getting too warm really at the moment. Right, let's leave it at that. Okay, it's been on for half an hour and I've turned it up to 20 watts now. So we're running 20 watts sine wave continuous. and it's putting out 80 milliamps on the bias, which again, perfectly acceptable, exactly what I'd expect. And don't forget 20 watts continuous. If you're actually playing, the average of your playing would be far, far less than this. This would be deafening if you were connected this to a speaker and you were playing at this level. I don't want to run it at any higher than 20 watts. Sine wave testing is very harsh on an amplifier. So the mains transformer is warm to the touch. Output transformer is obviously cool. Choke, tiny bit warm. And our resistors are fairly warm, I would say, but I've only had it on 20 watts. Ouch, yes, that's nearly too hot to touch now. That's because I've turned it up to 20 watts about 5 minutes ago. So I'm going to leave it on 20 watts for, well, 15-20 minutes. And if it's okay there, I think I can't do much more with this amplifier. It seems to be alright to me. Okay, we've been running half an hour at 20 watts continuous, which is a lot for an amplifier. The load resistors are just about too hot to touch. The transformer is warm. And it's all performing nicely. The bias is rock solid at 80 milliamps, hasn't even blinked. So I think this amp is okay. There's not much more I can do on it. For your interest, I have discovered it's a Marshall JCM800 lead split channel model 4210. That's just in case you're interested in things like that. Well, there you go. A bit fed up about this one, if I'm honest. I spent about 4 hours on it and achieved pretty much nothing. A lot of chasing my tail there, trying to work out why that plate voltage was so low. I did find someone on the internet who did a YouTube video, and he happened to also mention that his plate voltage was very low, and he was a bit surprised at 375. So that's what this amp is designed to run at. No idea why. We didn't find any problems with it. It's also got a bit of an annoying buzz at certain settings of the gain control. I spent a couple of hours chasing that with absolutely zero effect. I tried lead dress, I tried earthing, I tried every trick in the book, and nothing made the slightest difference to that buzz. So there you go. Not really sure what more to say about this amp. Fairly glad to see the back of it, if I'm honest. And on to the next one. Of course, the other thing about this is you can't charge the customer for 5 hours work to discover that the plate voltage is what the amp was intended to be. So, you know, you win some, lose some. Anyway, there you go. I've got another interesting amp to look at. It's a blues breaker, so that'll be the next video. But that also has got a fair old few things wrong with it, so I'm going to have to work down the list on that one. Okay, well, I hope you got something from this. I certainly learned something from the amp, so that's always good. And I'll catch you on the next video, and thanks as always for watching.